Safety is the main priority for all electrical utilities, and protecting personnel from the dangers of electricity whilst they are working inside the substation is essential. To do this, we use grounding equipment to make sure that when the equipment are being installed, modified, or maintained, electrical energy is rendered harmless. By the end of this section, you will understand why we need to ground equipment, and look at the main equipment that we use to do this in a safe and controlled way. The aims of the course today are: introduce the principles of why and how we ground an air-insulated substation. Look at the procedure for applying maintenance grounding connections on a typical circuit. Look at the different types of ground switches that we use. We normally ground a substation conductor or piece of equipment for the following reasons. Maintenance grounding, to allow equipment to be worked on or maintained safely. Operational grounding, to prevent voltages being induced on dead conductors from adjacent equipment. Let's look at maintenance grounding first. Maintenance grounding clamps and leads come in all shapes and sizes to fit onto the different types of conductors that we use in air-insulated substations. Here's some typical examples of the clamps that we use, and the types of grounding leads. Most electrical utilities insist that before maintenance grounding is applied to conductors or equipment inside a substation, the circuit needs to be tested first to make sure that it's dead and doesn't have a high voltage potential. To do this, we use voltage testers. These come in two forms. We have voltage testers that make a direct contact with a circuit that needs to be grounded. These tend to be used on distribution circuits up to 36 kV. Above this voltage level, it becomes too dangerous to make a direct connection to the circuit. At these higher voltage levels, we use voltage detectors that detect a voltage by being in proximity to the line that we intend to ground. Both of these types of detectors produce an audible alarm if voltage is present on the line being grounded. Let's see how we might apply maintenance grounding to work on a typical transformer in an air-insulated substation. Here's a typical transformer circuit with an isolator and circuit breaker on the high voltage side and an isolator on the low voltage side. The first stage in this process is to electrically isolate the equipment we intend to work on. To do this, we open the circuit breaker and then open the isolators on both sides of the transformer. When the high voltage isolator is fully open, it's physically locked out using a padlock. We then apply a lockout tag to warn people not to try and operate the isolator. This procedure is called a lockout tag-out system and consists of tags and hasps and padlocks to lock out the equipment and make sure it can't be operated. We then do the same on the low voltage isolator. The transformer is now electrically isolated from the system. The electrical operator uses an electrical tester to make sure that the high voltage conductors are indeed dead. He repeats this procedure on the low voltage conductors. A ground lead is now attached to the nearest ground spigot. This is directly connected to the substation ground grid. It's very important that we always connect the ground lead to the substation ground grid before we connect it to the equipment being grounded. Once the lead is connected to the ground grid, we use an insulated pole to connect it to the high voltage conductor. We then use the pole to tighten the grounding clamp to get a good electrical connection on the conductor. We then repeat this procedure on the low voltage conductor. again connecting the ground lead to the substation ground grid spigot before we connect it to the low voltage conductor. The transformer is now grounded on both sides, and a permit can be issued to work on the transformer. Whenever a piece of line or busbar is being worked on, it has to be grounded before the work permit is issued. The grounding points should be between the source of the electrical energy and the area being worked on. Inside substations, ground spigots are provided for the connection of one end of the ground leads, which are then clamped onto the conductor being worked on using the insulated stick provided. For high voltage substations, we also provide manually operated or motor operated ground switches that ground certain sections of the busbar. These are normally positioned on the substation isolators. They could be positioned on either side of the isolator. Here's an example where the ground switch has been positioned on the right-hand side of the isolator. The ground switch is given its own direct grounding connection to the substation ground grid. This has to be rated to carry the full short circuit current in case the ground switch comes into contact with a live conductor. The ground switch is prevented from closing until the isolator is in a fully open position. For manually operated ground switches, this is normally done using mechanical interlocking. For motorized ground switches, it is done via electrical interlocking, using the isolator auxiliary switches. We will look at interlocking in more detail in part 2 of this course. Let's now close the ground switch. When we have manually operated ground switches, we normally provide a ground mat for personnel to stand on as an additional safety feature. This ensures that the person's hands, which are in contact with the ground switch handle, and their feet are both at the same potential, so that if something does go wrong and the ground switch closes onto a live busbar, the current will flow through the ground switch ground connection rather than the person operating the ground switch. Here is a typical symbol for a ground switch. Firstly, we have a single-phase manual ground switch and a single-phase motorized ground switch. We then have manual and motorized three-phase ground switches. The decision on where to place the ground switches in the network depends on the operational requirements. Here's a typical double busbar transmission level substation. Let's look at the different parts of the circuit. Firstly, let's look at the busbars. We want to be able to maintain busbar number 1. To do this, we provide a ground switch on busbar number 1. The same requirement applies to all the other busbars. We need to be able to maintain all of the incoming and outgoing cables to the substation. We therefore need to provide feeder ground switches. Circuit breakers need periodic maintenance, so we need to be able to ground the conductors on both sides of the circuit breaker. So let's provide circuit ground switches. This is probably the minimum requirement for ground switches on this type of substation, but depending on the utility's permit requirements, additional ground switches may be provided. We also use operational grounding switches to ensure that certain parts of the network are dead. A typical example of where this is done is on parallel overhead lines. Most overhead transmission towers have 2 parallel circuits. If one of the circuits is energized and the other is not, dangerous voltages can be induced into the dead line. To overcome this, ground switches are positioned at each end of the overhead line circuit. Care has to be taken when opening line isolators and applying ground switches to overhead lines. as the induced voltages in the line from the adjacent circuit can create significant arcing. Here's a typical overhead line coming down to an air-insulated substation. For this reason, some utilities insist that all line isolators and ground switches are motorized. Other utilities provide a protective cover above the operating personnel to prevent any burning metal from falling onto them from the ground switch or isolator contacts. Isolators can be padlocked off to ensure that the circuit is dead, but there may still be voltages and currents induced onto the circuit from an adjacent circuit. Providing ground switches ensures that these are neutralized and that the personnel working on the equipment under maintenance are fully protected. Let's summarize what we've learned today. We ground equipment in air-insulated substations so that we can maintain or modify equipment safely, or when we want to make sure that a conductor has zero potential. To apply a manual ground on a circuit, a set safety procedure must be followed to minimize the hazard to personnel. Manual and motorized type grounding switches are provided in high voltage substations to ground sections of the circuit. You should now understand all about grounding equipment and how they are used to ensure personnel are kept safe whilst equipment is being installed, modified and maintained. I've attached some questions on today's section to test your knowledge.